So welcome back everyone, my name is Marco Morandocchi, I work at the Politecnico di Torino and I'm happy to chair this session of 2 talks now. First of all, on behalf of Patrick and the organization, I have to remind you that Bethany sent us all an email about the regulations for voting for posters, for the Best Poster Award. So please read that email and comply with it, so it's good if we can vote. Now it's my pleasure to introduce Professor Guang Lin from Purdue, and he's going to give a talk about Peri-Net analysis of crack patterns using deep neural networks.
And just a quick reminder before we start, everyone has a microphone, so any whispering will be amplified by 1,000 on his end. So please, everyone, hold all conversations till the end. All right, thank you. Go ahead.
Okay, please.
Okay, so hello everyone. So my name is Guang Lin. So today I will talk about how to using the deep neural network to do scientific computing. So I'll give some examples. First one, let's look at what we can do to first motivate. The motivation is try to using deep learning to kind of replace the finite element solver and achieve the real-time prediction of PD solutions and quantify the uncertainty, and also basically give a certificate to the deep learning. And along this goal, we have developed a tool that's called a convolutional PD-UQ network that is able to quantify the uncertainty in the deep learning of PD solutions in arbitrary domains. So we have this paper published in the Journal of Computational Physics. Let's first look at the problem setup. So this problem setup is first from left to right is a simple problem solving a Poisson equation on a circle. Basically, I tried to giving me a heterogeneous of F. I try to predict the solution of the U, and then we go to the middle part is the solving Poisson equation on rare domains. And the last problem is a nonlinear Poisson equation. We solve it on the rare domain as well. So the problem is basically I try to achieve here is basically giving a image of F. We want to predict the solution of U. Basically, neural network will provide the image of U. Okay, so that's the problem setup. Different from the finite element setting is that we try to solve it in finite element. So we have to basically try to discretize the problem, generate the mesh, then apply a numerical solver to solve this problem. However, if in the deep learning setting, we just need an image to image mapping. Basically, give me image of F, I can provide an image of U directly. So that's the difference. So let's first we need a theoretical framework to be able to ensure that we can use deep learning to predict the PD solutions. So for the elliptic problem, we can employ the Green's function for the Laplacian on a unit disk. So that way we can basically provide a one-to-one mapping. Basically, we're giving the F, we can, using the Green function, integrate it with the function F, then we can obtain the solution of the U. So that means we have a one-to-one mapping from F to the solution of the U. So this provides us the feasibility of using the deep learning to predict the solution U given the flux F. So that's the motivation and providing the approximation map. Okay. So we basically eventually go to achieve is image-to-image predictions. Okay. So that's the motivation. To achieve that, we need basically to define basically loss functions in the optimization. So the loss function, there's many different ways to define the loss function. One of the ways is the standard the mean square loss. Is we define by the one hat is what the deep learning prediction, and the y is basically the sample data. So we try to do a mean square loss, compute the L2 now, then we try to use that as an indicator for the loss function. So this is the standard loss function to basically measure the measurement points, how the prediction compare with the observation data inside the computational domain. And if we also want to enforce the boundary, so then we need to add the boundary part. So in the loss function, we have two parts. So the first part is interior points. The second part is to calculate the boundary conditions. So the lambda here is basically a logarithmic multiplier. So we can basically is weighting parameters to put these two together. In addition to this traditional loss function, we also introduced a new loss function, so-called probabilistic loss function. So you can say we basically using a Gaussian distribution to approximate the loss function. So the Gaussian distribution inside the exponential part is the predicted mean, and so the predicted variance, right? So we basically have this y is the prediction, right? So we basically want to estimate the y. Then we take the negative log likelihood of the loss function, then we basically obtain a probabilistic loss function represented by this log likelihood. So what's the benefit of using that is, as you can see here, from left to right, that's basically present during the neural network training process. Initially, due to the parameter is not estimated very accurately, we have a larger variance. So that's why the probability distribution is a fat. We have larger standard deviations. But through the training process, you can see the standard deviation getting smaller. So then we have this basically an indicator tells us how well our character estimation is and how well this neural network training process is. This gives us a good indicator. So here is the neural network architecture we built up for solving the PDE. So from the left is the picture of the F. As you can see, it's a heterogeneous 128 times 128 image. Then we go through this network, so-called encoder-decoder network. So from the left to right to the middle, that is the encoder part. We basically encode a 128 by 128 image to a 4 by 4 image. So that is the encoder part. Then we have a decoder part. Is basically decoder this 4 by 4 information to a 128 to predict the solution of the. And different from the traditional encoder-decoder network. So as you can see on the right of the network, we have two channels. One channel is predicted the mean, and the other channel is predicted the log standard deviations. Basically, it's predicted the error bars of the neural network predictions. Then we basically can look at the error bar, how large the error bar is, and then basically give us a good indicator of how well this neural network prediction is. We use it to certify the predictions. Here, basically, some numerical results we show here is basically present us the errors. So on the left, basically, is showing you the Poisson on a circle on different domains. The last one is nonlinear Poisson. So there's 3 loss functions we have tried. The first is probability loss function. The middle ones, we do the mean square loss function, but consider the boundary. We choose lambda to the 0.1. And the third one is we don't consider boundary, only consider interior point, choose lambda to 0, then we're using the MSE errors. So you can see the error we can achieve using L1 relative error or L2 relative error. So we can achieve either 10 to the minus 3 errors or 10 to minus 4 errors. And also we can see the probabilistic loss function will give us the best estimation compared to the mean square loss functions. And then also this error, you can see overall the error is pretty small. This basically indicates that we can using the deep neural network to predict this like a Poisson equation. It will give us a pretty good accuracy. Now let's look at some contour plot. So on the left is the prediction, right? Next to it is the true solutions. As you can see, looks very similar. And in the bottom, we basically present the mean prediction, also the error bar represented by the two standard deviations. So as you can see, by doing that, we basically to know where, in which area we have large errors. Okay. Now basically, let's look at compare the speed. Okay. So basically, average, right? So if we use the Phoenix solver to solve in parallel using parallel machines, we need about 0.05 seconds to solve one test case. And if we're using the neural network to predict, we only need like 0.01 second to make prediction. So this basically satisfies the real-time prediction criteria. So this basically indicates us that using neural network, we can using that to predict PDE solutions on the fly. And currently we are working on to try to apply this technique to the variable coefficient differential operators and more general boundary conditions such as inhomogeneous boundary condition, Newman, and mixed boundary conditions, and also making prediction with noisy and discontinuous input data. This is here basically I present is how we can use a deep neural network to solving the PDE to reduce finite element. So the next part is think about what the finite element cannot do is basically try to predict the material failure and the fracture propagations. So that's why the goal here is try to replace the computationally expensive fracture mechanics solver and to using the neural network to predict of material failure. So to achieve that, we have developed a tool called Peri-Net. So that's going to help us to do deep learning of material failure and the fracture propagation. So here, the first slide is basically showing you the motivation. So why do we need this study? So as we can see, like we have cell phones, right? If cell phone fell down, it can break, can generate fractures. So can we predict that? Also, if you look at the bridges, right? How can you predict the bridge fracture propagate over time and the loading conditions, right? So can we predict using deep learning to predict that? So that's the motivation. And also think about the power plant and the nuclear power plant, also the thermoelectric power plant, the blade, the fracture mechanics, right? So can we using the deep learning to predict such kind of material failure? So here is basically the setup of the problem. So first of all, we basically look at the inverse problem. The inverse problem, the idea is if you look at the lower figure, so basically there's a lot of like a host generated. So like some criminal using like a machine gun to beat down the wall, you can say generate a lot of hosts there. So can we using that to identify like what's the shooting locations, which kind of size of the bullets, right? So which gun they use, what's the shooting angle, and what's the bullet velocity, etc. Can we predict that? This is the inverse problem. And also we can look into the forward problem is what if I tells you that basically using which kind of like bullets or which location I hit, so can I predict the crack patterns? So this is a forward problem. So we try to study in both scenarios. So the first setup for the forward problem is we employ the lamps, and we try to employ this flying disc problem. So we vary the shooting locations around this red circle. So basically, we're changing these shooting locations with the two inputs x and y. Then we want to predict the fracture patterns. So what we did is we generate 1,000 of data by varying these shooting locations. Then we run the cases using lamps, run these 1,000 cases, we generate the data set. Then we employ this data set for training our neural network. So here is basically showing the architecture of the convolutional neural network. So as you can see on the left is the XY locations of the shooting locations. Then we on the right is basically predicted the fracture patterns It's a 64 by 64 image. And as you can see, this neural network include a fully cranked neural network, and the reshaped network, and the 3 by 3 convolution, and the 3 by 3 convolution without regular functions. And as you can see, the training error is around 0.06, and the test error is around 0.01. So you can see we can achieve pretty good accuracy. Now let's look at the mean square errors. So this is the training step. The x coordinate basically shows the training step. The y basically shows the mean square errors. The blue line basically showing the training error, and the orange line showing the validating errors. Okay, as you can see, we in the training step around like 500K training steps. So as you can see, the error was dropped from like 0.015 dropped to around like 0.09. Okay, the mean square error decays through the training steps. Okay. Here basically showing you the results. So on the left, we basically show the using peridynamic predictions, simulation results. On the right, it's basically using the neural network predictions. If you compare these two results, you can see the overall, basically the main fractal pattern, it was captured by using the deep neural network. However, if you look at this small fractal part, it seems like it's a little bit smeared compared to the simulation done by the peridynamic. I think the reason is because the seems like the fractal mechanics like very sensitive to the shooting locations. It's also it is a very nonlinear problem. So that's make the neural network to predict the small fractal patterns. It has the difficulty and it's got smeared. And the benefit by using deep neural network is the speed. So if you look at if we're using the peridynamic, the computational time for one simulation, it requires around 7.5 seconds. However, if we're using the convolutional neural network, it will only require around 10 to the minus 3 seconds. So that's the computational saving using the neural network. So that's make us be able to do this some real-time predictions of the fracture patterns. So this basically show is a forward problem. Now we try to make the problem more complicated. So basically, in the first example, I basically show we only change the shooting location x and y. Now I also want to changing the like bullet size and also the bullet speed. So here what we do is we change the radius of the bullet, okay, also changing the velocity of the bullet and also the hitting location of the bullet. So we have basically 3 parameters can be varied. Okay, so because we have a larger degree of freedoms, so we require generating more data. So that's why we generate around 15K data set. So that's using the lamps to generate the data set. And then we use this data set to train our neural network. So here's some numerical results. As you can see, the left is the peridynamic solutions, and on the right is the convolutional neural network predictions. So you can see in the these red areas, the shape is very similar to the peridynamic predictions. Again, you can see the small fractional area, it was blurred. Okay, so that's due to the sensitivity to the shooting locations, also due to the strong nonlinearity of the peridynamic problem. Okay. So this is we changing the shooting locations. So you can see a similar thing happen here. So the left is the peridynamic solution, and the right is the predictions. Right? You can see basically the main fracture pattern with the neural network can predict it pretty accurate. Okay, and so now we move to the inverse problem. The inverse problem setting is given a fracture pattern, then we try to using neural network to go back to identify what's the shooting locations, what's the bullet size, what's bullet velocity, etc. So to do this inverse problem, so we generate a 7200 data set, and using this data set to train a neural network. What we do here is basically we try to inverse the radius of the bullet, the velocity, the angle, also the hitting locations. Okay. Then basically is we identify the 8 different parameter settings, and we're using this to basically do the inverse problem. So this is the neural network architectures. So given an image of the fractal pattern, then we go through a convolution layer, the max pooling layer, another smaller size convolution layer, then max pooling, then random function, then finally we go to a softmax to do the feature classification. So this basically is first we do the feature extraction, then in the last 2 layers we do this feature classification to classify the parameter settings for the fractional problem. Okay. So here is basically numerical results. On the left, basically show the basically training iterations from 0 to 25. I can say on the y coordinate, it basically shows energy decay over the iterations. So the blue line is basically the training arrows, and the dash orange line is the validation data set arrows. So you can see the arrows decay over the training process, and also the validation arrow is slightly bigger than the training arrow. This makes sense. And also you can see this arrow we can achieve success rate over 95.6. So accuracy in the right classification. So that means like we can using the deep neural network to be able to do this kind of inverse problem to kind of classify, okay, identify this giving a fracture image. We are able to identify what's the parameter setting for causing this fracture. So using this, we can basically to speed up solving the inverse problem. So I think neural network has a lot of potential on both the forward problem and solving the inverse problem. And in particular for the inverse problem, because it's more challenging to using traditional like 5M solvers to solve this such kind of inverse problem. However, neural network has its own like unique advantage. Okay. And finally, I want to conclude. So here, basically, in this talk, I have present convolution PDE-UQ network to quantify the uncertainty in the deep learning of the PDE solutions on an arbitrary domain. Okay. I also present a Peri-Net to analysis of crack patterns on the disk. And finally, these two deep learning tools can greatly reduce the computational cost and provide accurate predictions on both predicting the PDE solutions and also predict the material failure and the crack populations. Thanks for your attention. Any questions?
Thank you very much. Are there any questions?
Can you hear me?
Yes.
My question is regarding the first part of your talk, a solution on the Laplace equation. You implemented the boundary conditions as a constraint on the objective function that you're minimizing. Does that mean that for every training cycle, you need to basically implement a new boundary condition? For every change in boundary condition, you'd have to go through the training process again?
Yes, because this, let me show you that. So basically, yes. So in the training, we basically fix so this is the part, right? So this is the part of how we define the loss function, right? So in the loss function, we import the boundary conditions. So this is like virtual boundary condition we enforce. So to satisfy the boundary condition, right? If you change the boundary condition, then basically you have to change the definition of the loss function, right? So and you still can using for example, I already trained a neural network to produce a solution on one particular neural network. So if you want to change the boundary condition, then you need to do updating, right? You basically modify the loss function to bring actual data to basically you can using this already trained neural network parameter setting as an initial start point, then using that to basically using the new data set, right, basically to update.
So that's like transfer learning.
Yeah, it's like transfer learning, yes.
So, you know, I think I understand that, you know, the predictions that you presented are, you know, you're not incorporating the timing of the training in any way, which is a little bit unfair in the way you present, like when you compare, you know, the Phoenix solution to the GPU, you know, neural net, because you're just doing the forward problem to the trained neural net. But what about the training? How long does that take?
Yeah, I agree with you. But the advantage, so that's the catch, right? So basically, I can separate the time into the offline training and the online prediction, right? I agree with you. The offline training take a much longer time, right? But the online is like very quick, right? So, but however, if we have the offline training already done, right, then we can basically like have an app, for example, like on the cell phone, right? You can just use from your cell phone to make prediction of a complicated PD solutions, right? So because every day you use basically this, you just need to use this trained neural network to make a
But
kind of prediction.
you also have to retrain because you changed the boundary conditions or the geometry of the problem, right? So there's a little bit of overselling in my opinion, but
yeah. So we already so I think that so right now, of course, this problem setup we fix the boundary conditions. But we can change domains. We can try different domains. We already basically that depends on how well you train your data set, right? Basically, if my data set already include all kinds of different boundary conditions, then I don't need to like retrain on new boundary conditions. So that's
I think part of the point here, though, is that as you try to increase the generality of the neural network and its ability to make predictions, the size of the training set that you need to provide grows considerably.
Yeah, I agree with you. Yeah, that's the overhead, right? That's the overhead for the deep learning. Yeah.
Okay, if there are no other questions, we can thank Professor Lin again. Thank you.
Thank you.